We are very proud and honored to have you, Sandra Rivera, as our keynote speaker for this year's Embedded World Conference. Sandra is Chief Executive Officer of Altera, which was an Intel company until the end of last year. Sandra leads Altera focused on the development of field programmable gate arrays, the FPGAs, that are used across data center, communications, industrial, automotive, aerospace, and defense market. Before assuming her current role, Sandra led Intel's data center and AI group, where she guided development of data center products. Sandra also drove Intel's overall AI strategy and product roadmap, and in 2023, she was named by Time magazine as one of the industry's most influential people in AI. From 2019 to 2021, Sandra was Intel's Chief People Officer, leading the company's human resource organization worldwide. She also led Intel's network platform group from 2017 to 2019, driving the transformation of network infrastructure to Intel-based solutions. Sandra joined Intel in 2000 as a marketing director after the acquisition of Dialogic Corp. Earlier, Sandra co-founded and served as president of the CTI Authority and served as president of the computer telephony division at Catalyst Telecom. Sandra holds a bachelor's degree in electrical engineering from Penn State University and sits on the Equinix board of directors and is a member of the University of California, Berkeley's Engineering Advisory Board. The title of Sandra's keynote is Pushing Boundaries, Flexible AI at the Edge. So I believe this is very much in line with what we want to have here. So very warm welcome to you, Sandra. It's a pleasure and an honor to have you here. Stage is yours. Thank you.
Good morning, and welcome again to Embedded World. I always love coming to this conference and all the energy and all of the innovations that we see in embedded systems that are driving and impacting the world around us. As developers, we come to Embedded World to see all the latest innovations, from hardware providers to software solutions providers to experts in design services. And when you walk the exhibit floor, you're going to see a broad mix of companies that are showcasing the latest breakthroughs in embedded innovations. And this year, the topic that nearly everyone will be talking about is AI. And that's because AI is transforming everything, with generative AI models quickly being deployed by businesses of all sizes to enhance efficiency, customer experience, and accelerate decision-making. Companies are investing hundreds of billions of dollars to meet the AI demand. And they're building out large AI clusters across the infrastructure. In 2024 alone, Meta, Amazon, Microsoft, and Google invested collectively over $300 billion in building out their AI infrastructure, while Apple recently announced that they're going to invest over $500 billion over the next 4 years. A question that this poses for all of us is, once these models are trained, where do we go from here? What's next for AI as millions of optimized models will be processing data virtually everywhere? When I talk to customers, the thing that I consistently hear is that customers are looking for flexibility and choice when developing their AI solutions. And it's a valid request because when you look at every major technology transition, from the internet to client-server to cloud computing, they have all been based on heterogeneous architectures and an open software stack. To unleash the full potential of AI, developers must have access to the AI infrastructure, services, and applications that make it easy to deploy AI solutions at scale. And that's the journey that we're on. To talk about where we're going, I think it's important first to understand how we got here. As a technology, AI has existed for over half a century. Classic machine learning and neural networks were introduced all the way back in the 1950s and remained relatively stagnant for many years. There wasn't a lot of new innovation until CNNs and RNNs were introduced in the 80s and 90s. And then again, a couple of decades where not a lot of innovation happened. But the introduction of AlexNet in 2012 changed the game, triggering an explosion of AI developments. Simultaneously, advancements in semiconductor manufacturing technology, networking, memory technologies, and innovations in software solutions and more sophisticated tools helped drive AI forward. With improvements in transformer-based deep neural networks, there's been a flood of generative AI innovations and systems which have been catalyzed, of course, by ChatGPT. Now, everyone with a computer has access to a user-friendly interface to interact with AI for various tasks like writing, editing, learning, and of course, coding. Today, we're living in the AI era where generative AI and intelligent computing is quickly becoming ubiquitous in all our lives. And a key enabler in this shift is the deployment of AI in edge applications, the intelligent edge. The edge brings AI out of the data center into systems and devices that are closer to the user, where most of the data is actually created and consumed. Market research firm Gartner forecasted that within the next year, approximately 75% of enterprise data will be processed at the edge. And there's three fundamental reasons that are driving this shift in AI processing, and that's cost, speed, and security. The process of moving data back and forth between the edge and the cloud can be expensive. Edge AI delivers meaningful cost savings by limiting data transmission and allowing operations to be scaled down to intelligent endpoint devices. The speed at which AI can operate directly impacts the performance and usability of these edge devices. Sending large volumes of data to the cloud and back makes many use cases impractical or even dangerous. For example, a factory robot must be able to respond in real time to situations that could impact the safety of humans that are also working in that environment. And from a security perspective, there's often a need to keep data on premises or in geo for both regulatory and IP security reasons. As devices and machines proliferate at the edge, AI will be the dominant workload driving new functionality, new insights, and capabilities bounded by cost, speed, and security constraints. For embedded developers, the intelligent edge creates a unique and challenging environment. Contrasted with data center infrastructure deployments, embedded edge devices have more stringent size, weight, and power constraints. If you're designing a battery-powered surveillance camera that must operate under 4 watts in a 100 millimeter squared form factor, you're clearly working in a physically bounded environment. And these systems require performance and real-time processing as well. Modern factory floors and autonomous systems contain an array of advanced sensors and cameras that use sensor fusion to accurately process large amounts of data. The compute must be able to execute multiple tasks in parallel to efficiently manage this data in real time using tested AI models. Another challenge that developers face is dealing with changing standards and innovations. Since AI is such a rapidly evolving workload, hardware and software must be able to become flexible and agile for embedded developers to choose what they need for their specific use cases in the edge AI landscape. Today, there are three primary silicon options used to accelerate AI workloads: general-purpose processors such as GPUs and CPUs, custom ASICs, as well as FPGAs. And each of these logic devices has its unique benefits. Here, I'm showing the qualitative advantages of these accelerators from an efficiency perspective using 4 classical machine learning use cases. The vertical axis shows accelerator efficiency as measured by performance per watt. As you can see, application-specific accelerators are very efficient at performing a specific AI task. But their efficiency drops if they run a workload that they were not specifically designed for. This is the route to go if your workload can be supported in a fixed function device and you have the budget and volumes to justify the development time and cost of a custom ASIC. GPUs and CPUs are broadly used today, of course, to accelerate AI workloads based on their general purpose nature as well as their ease of deployment. The vector processing capabilities of a GPU make them highly efficient at accelerating AI tasks like scientific computing, image processing, and simulations. A third option are FPGAs, which provide relatively consistent accelerator efficiency across a diverse range of neural architectures. This is due to an FPGA's inherent high-performance architecture and their flexibility, which allows users to optimize hardware for specific AI tasks. In many cases, the customization provides higher performance and improved power efficiency over more general-purpose options. And for businesses, of course, this means a lower total cost of operations. Compared with a fixed function accelerator like an ASIC, the reprogrammable nature of an FPGA allows users to reconfigure the silicon in their system requirements as they evolve. For edge use cases, FPGAs provide a scalable platform that can be customized from small form factors and low power envelopes to larger footprints, with the added benefit, of course, of very long life cycles. Here, I'm showing a high-level floor plan of a modern FPGA. At the heart is a programmable fabric. This includes customized silicon that's configured by the designer and can be reprogrammed as system requirements evolve. Users can optimize the FPGA's resources for specific use cases, delivering improved performance and efficiency. And for workloads like AI, the fine-grained FPGA architecture can support parallel execution of multiple operations. In Altera's latest FPGAs, we infuse the fabric with AI tensor blocks to accelerate AI workloads. This enables deterministic, low-latency, real-time processing for models deployed in embedded applications at the edge. And surrounding the programmable fabric are many reconfigurable subsystems. These include high-speed general-purpose I/O and memory interfaces to get data in and out of the FPGA quickly, built-in transceivers supporting many different networking protocols, integrated processors to run CPU tasks in chip, and a secure device manager to keep data protected. Virtually everything in an FPGA is configured by the user for their specific use case. Like AI, FPGAs have been around for decades. And in that time, they've gone through a significant evolution supporting the continued advancements in AI technology. This chart shows how FPGAs have evolved over the past decade to support the increasing compute demands driven by AI. When AlexNet was introduced, the FPGA industry started building single-precision 32-bit floating-point numerics support into the FPGA architecture. This gave users a good balance between precision and computational efficiency. Supporting more advanced floating-point formats like bfloat16, FP16, and FP19 provided an even greater balance between computational speed and precision in machine learning and deep learning applications. A key advancement was delivered by Altera when we added AI tensor blocks into our FPGA fabric. These blocks are specifically optimized for matrix multiplication that are used heavily, of course, in AI model inference. Since FPGAs were introduced with FP32 operations in the silicon more than a decade ago, we've been able to deliver a 140 times gain in FPGA compute density. And this is a result of the extensive compute resources in the FPGA, the ability to support fine-grained parallel processing, and user-customizable architectures. FPGAs have quickly become a practical solution for accelerating AI inference, especially at the intelligent edge, where low latency and real-time processing are required. Today, FPGAs are pervasive across virtually every industry, from the cloud to the intelligent edge. Within the data center and network, FPGAs are used to support several AI functions, including the preprocessing of data, offloading tasks like encryption and storage acceleration, and operating as a NIC in large AI clusters. But it's within the intelligent edge that FPGAs are increasingly being adopted. Many edge workloads, like vision and video processing, have already consolidated into an FPGA. And as embedded developers look for ways to incorporate greater levels of intelligence in their industrial, medical, or autonomous vehicle applications, they're using the FPGAs already running in their systems to deploy their AI models. They're taking their FPGA that they have, and they're deploying the AI that they need. I'd like to illustrate how some of these embedded and edge use cases operate, and show you how FPGAs help address the challenges of embedded developers today. We'll start with a smart factory, where FPGA-based robot control systems are used extensively to enable highly efficient operations. Today's multi-axis robot arms use multiple sensors, cameras, and advanced computer vision techniques to perform tasks like inventory management and defect detection. Smart factories also have human-based manual checks in the process, so ensuring the highest levels of safety in these environments is paramount. FPGAs used in these environments because they efficiently manage continuous data streams using sensor fusion and tight control loops. Their fine-grained real-time control drive precise motor control algorithms. And now, with built-in AI capabilities, FPGAs provide even greater value to businesses looking to modernize their infrastructure. FPGAs are opening new approaches for AI in robotics at the edge, like fusing machine learning capabilities into sensor pipeline to intelligently manage inventory and autonomously look for defects. And as robotic systems evolve, embedded developers can future-proof their systems by customizing their FPGA-based platforms to support higher quality camera sensors and deploy next-generation image processing capabilities. Turning now to autonomous vehicles. In autonomous vehicles, the flexibility and performance efficiency of FPGAs are reshaping this rapidly evolving market by driving future mobility innovations and infrastructure advancements. From limited operational domains to free-ranging geographies, autonomous systems are characterized by these diverse environments that we must operate in. And we are confronted with a dynamic range of algorithmic and processing complexities across this range of environments. A common approach today is to use a general-purpose processor or to develop an ASIC to each specific domain characterized by the system's sensor modalities, such as high-definition video, cameras, LiDAR, and radar. These systems also demand accuracy and real-time processing. Embedded developers are increasingly turning to FPGAs as a flexible alternative to accelerate real-time processing and manage complex computations in autonomous systems. Their inherent parallel processing capability perform real-time computations of data coming in from multiple sensors and cameras. And by integrating deep learning AI models into an FPGA-based system, developers can enable critical functions such as object detection, collision avoidance, and real-time decision-making. Paired with a processing subsystem, FPGAs deliver a complete scalable platform for systems as varied as agricultural robots to city-crossing truck fleets. Turning now to the medical industry. FPGAs are helping improve patient care across many domains, from small battery-operated patient monitors to large lab equipment and CT machines. In the field of endoscopy, the performance and low power of an FPGA help detect anomalies in real time, providing instant feedback and alerts to healthcare providers. In medical imaging, FPGAs are used to enhance image quality, processing speed, and system efficiency. Developers use FPGA-based platforms to manage the data coming in from the camera sensors and video pipelines. And by running deep learning models trained to analyze images and video feeds, these FPGA-based systems help enhance patient outcomes by detecting polyps, lesions, and tumors. And the information can be shared with medical professionals in near real time so they can act upon that data. FPGAs integrated with AI are transforming the healthcare industry with capabilities like real-time image analysis, continuous patient monitoring, and personalized diagnostics. They're uniquely suited to accelerate these AI-driven tasks directly at the point of care, providing high performance, adaptability, and energy efficiency. And these are just some of the areas where FPGAs infused with AI help address many of the challenges that embedded solutions providers face while bringing improved results to edge applications. But the real unlock of programmable logic comes from software and the ability to rapidly convert and optimize trained AI models that are deployed on an FPGA. Historically, FPGAs have been challenging for many software developers because they require working in the domain of low-level hardware description languages and unfamiliar design flows. For software developers that are used to working in Python or C, this can be daunting. But over the years, our industry, has made a lot of progress to simplify the FPGA design process, especially when it comes to software developers accelerating AI workloads on an FPGA. Today, Altera is pioneering the age of FPGA, which is the tight coupling between programmable logic and AI that enables embedded developers to add AI capabilities to an FPGA. Through the software tools available, developers can remain in the design environment that they're familiar with while using industry-standard tools, frameworks, and models. This design flow not only helps AI inference IP generation targeting FPGAs, but also facilitates the collaboration between data scientists and FPGA engineers to create highly optimized FPGA AI platforms. It all starts with AI model development, something every AI developer is familiar with. In the FPGA AI development flow, data scientists choose an AI model that they want to accelerate, such as a neural network for image classification. They use industry-standard frameworks like PyTorch, TensorFlow, or Onyx to train the model and refine it. At the end of this process, they have a trained AI model, which now needs to be optimized for an FPGA. AI developers input their trained AI model into OpenVINO, the OpenVINO model optimizer that creates an intermediate representation of the data. OpenVINO is an open-source toolkit used to develop deep learning models on a variety of hardware architectures. The model optimizer lets a developer tune their design to meet their performance goals. It also ensures that the design will fit within the resources of the target FPGA. Next, an FPGA AI tool takes this data as input and generates AI inference IP. The tool automatically looks at the design and provides recommendations to achieve the optimal area and performance targets. The tool also enables the AI developer to perform software emulation to check the model's accuracy. Once the performance and accuracy are met, the AI inference IP is handed off to an FPGA engineer who can add the IP to the target FPGA design using a standard FPGA design tool suite. You now have at your fingertips a highly customizable AI inference accelerator that delivers the performance, low latency, and low power that intelligent edge devices require. And because FPGAs support long life cycles of 15 years or more, your FPGA-based AI accelerator is future-proof. You can qualify and deploy your design while continuing to enhance its features and capabilities for many years to come. We recently talked with VTech to build an FPGA-based medical imaging system using our FPGA AI development flow. VTech is a Paris-based video solutions provider whose services help enterprises deploy end-to-end video streaming solutions. I've invited VTech's Eric Denau to share more about our work together.
Thanks for having me, Sandra. VTech is a leading provider of video technology solutions. We recently worked with Altera, the leading medical company, to bring artificial intelligence into the operating room. Using the trained AI model based on the company's proprietary datasets, VTech engineers worked with data scientists to integrate and deploy the AI model into the Altera FPGA that the customer was already using for video processing. The data scientists used the Altera FPGA AI suite and other software to convert the trained AI model to an FPGA-optimized AI inference IP that our team easily incorporated into the standard FPGA design flow. Altera's AI software was the key, since it allowed back and forth collaboration across all parties involved, so we could finish the project quickly. Using FPGA-based AI acceleration has proven to be highly effective in improving AI performance in edge applications.
That's pretty good, right? Yes. And thanks to Eric and VTech. There are many other examples like this one from companies harnessing the performance, flexibility, and efficiency of an FPGA-based solution to drive greater intelligence at the edge. AI is a rapidly evolving technology that demands solutions which are scalable, high-performing, and future-proof. And deploying AI also requires a holistic approach across hardware, software, and application domains, incorporating the innovations, products, and services of many companies across the industry. There's an extensive partner ecosystem who have built FPGA-based solutions, IPs, and software, all to assist you in your development process. And the developer environment is built on industry-standard frameworks and libraries that many of you use today. These solutions are built to ease the development process and accelerate design time and get to market quickly. And many of these companies are demonstrating their solutions here at Embedded World. I encourage you to visit their booths and get started evaluating FPGAs on the extensive range of reference boards and design kits that are available. And I also encourage you to stop by Altera's booth to see some of our latest FPGA AI demonstrations and innovations. As I mentioned at the start, we are on the early days. We're in the early days of truly understanding the potential of AI. We're already seeing progress across 3 critical vectors. First is with accessibility and affordability. AI infrastructure in the cloud or at the intelligent edge is readily available to process vast amounts of data in near real time. And additional AI hardware options like FPGAs are helping to increase both availability and affordability. Second is better access to data and improvements in AI models. AI systems thrive on diverse, high-quality data. Today, there's an estimated over 40 billion connected devices collecting over 400 million terabytes of data every day. This data, combined with breakthroughs in advanced AI models, is making AI more adaptable to real-world applications. And lastly is the increasing integration of AI into our everyday lives. Our smartphones, wearables, and vehicles already have AI functionality built in. And as more devices integrate greater levels of intelligence, we'll start to see a seamless experience where devices and systems make autonomous decisions based on real-time data. Making AI ubiquitous requires a concerted, collaborative approach across the entire embedded community. We're committed to working with you to make AI more accessible across a device range of edge systems that are optimized for low power, high performance, real-time processing while ensuring privacy and security. I invite you to join us on this journey. Thank you.